Areas of surfaces of revolution. All right, let f be a smooth, non-negative function on an interval AB. What we want to do is find the area of the surface generated by revolving the curve about the x-axis. All right, so we have our function and we have our interval. Now let P be a partition of that interval AB. So P is going to slice up our surface area like this. If we look at one of the slices, so here's our kth slice, that shape looks like the bottom half of a cone, and that is called a frustum. And we can find the surface area of a frustum of a cone. The formula for that is that it's equal to pi times the sum of the two radiuses times the length of the slant height. All right, and we know how to find that length because we know how to find the distance between 2 points. So we get that the surface area of that slice is approximately equal to the area of the frustum. And if we put in our formula for L, we get that surface area becomes pi times f of x sub k plus minus 1 plus f of x sub k, all times the square root of delta x sub k squared plus f of x sub k minus f of x sub k minus 1 squared. All right, so this right here is the change between your x coordinates. This right here is the change between your y coordinates. All right. So now by the mean value theorem, we know there's a point c sub k in that interval, in the kth interval, such that the slope of the secant line connecting the 2 points is equal to the derivative of our function evaluated at that c sub k. We can solve this by multiplying both sides by the denominator to get f of x sub k minus f of x sub k minus 1 is equal to the derivative of the function evaluated at c sub k times delta x sub k. And we're going to take this right here and plug it into the formula for our s sub k's right here. So that gives us that the surface area of our kth slice is approximately equal to pi times f of x sub k minus 1 plus f of x sub k times the square root of delta x sub k squared plus the derivative evaluated at c sub k times delta x sub k squared. Now if you look under the radical, both terms here have a delta x sub k squared. So we can factor that out and then take it out of the radical to get this as our approximation for the surface area of our kth slice. All right, now what we have is we want to look at this. This value right here is the average of the two y values, right? And we know that that value is going to be between f of x sub k minus 1 and f of x sub k. So using the intermediate value theorem, since f is continuous, we know there exists some point, let's call it d sub k, in our kth interval, such that the average value here is equal to f at d sub k. Or you can multiply both sides by 2 and plug it into our formula to get that the surface area of our kth slice is approximately equal to 2 pi f evaluated at that d sub k plus, times the square root of 1 plus the derivative evaluated at c sub k squared times delta x sub k. All right, so remember d sub k and c sub k are both some point in the kth subinterval. All right, so that means that the total surface area is approximately equal to the sum of the surface area of our slices, or actually it's equal to that. Those are approximately equal to the sum as k goes from 1 to n of this formula. All right, so now we expect that as the norm of our partitions goes to 0, that the true surface area is going to be equal to this formula. Now, if C sub k and D sub k were the same, this would just be a Riemann sum and therefore the definition of a definite integral. But we don't have that C sub k and D sub k have to be the same. But it can be proved in higher calculus, and we're going to do, that the limit is indeed the definite integral. So that leads us to give this definition for surface area. Let f be a non-negative smooth function on the interval AB. Then the surface area S generated by revolving the portion of the curve y equals f of x between x equals a and x equals b around the x-axis is the integral from a to b of 2 pi times f of x times the square root of 1 plus the derivative of f squared. And as we saw with our other volumes of with the volumes of revolution, there's a corresponding formula if we want to rotate around the y-axis. All right, so let's go ahead and do an example. In our first example, let's find the surface area generated by revolving the curve y equals the square root of 1 minus x squared over the interval 0 to 1/2 about the x-axis. All right, so here's our solution. The graph of the curve is an upper semicircle of radius 1 centered at the origin. So here's our upper semicircle of radius 1 centered at the origin, and we're only looking at x between 0 and 1/2. So it's this portion of the curve right here. All right, for our formula, we need to know our function, the derivative of our function, and once we have those, we can just plug them into the formula. Our a is going to be where we take our slices. We're starting at x equals 0, and we're slicing up to 1/2. So a is 0, b is 1/2, and then 2 pi, here's our function, times the square root of 1 plus our derivative squared. Now, if we simplify what's under the second radical here, we get that this term right here becomes this. And now if we put everything here over a common denominator and simplify it, we'll find that it's equal to this. And once we've done that, this and this, when they multiply together, give you 1. So we end up taking the integral from 0 to 1/2 of 2 pi dx, which you all know is equal to pi. All right, so let's look at another example. Let's find the surface area generated by revolving the curve y equals the cube root of 3x from 0 to 2 about the y-axis. All right, so here I'm revolving around the y-axis. So I want to find x as a function of y. So I'm going to take the equation they give us and solve it for x. And then once I have that, I need to know its derivative. So I get dx dy is equal to the derivative of this, which is y squared. I take that information and I plug it into our formula for surface area. Remember, we're integrating with respect to y, so our slices are going like this. So we're starting at y equals 0 and going up to y equals 2. So our limits of integration are 0 to 2. Then 2 pi, here's our function, times the square root of 1 plus the derivative squared. We go ahead and simplify everything. And now to find this integral, look here, this is y cubed, this is y to the 4th. Let's make a u substitution of u is equal to what's under our radical sign. That means du is equal to 4y cubed dy. And let's just get rid of this 4 here, so we get that 1/4 du is equal to y cubed dy. Now when we do a substitution on a definite integral, we also have to change our limits of integration. So when y is equal to 2, we get that u is equal to 17. And when y is equal to 0, we get that u is equal to 1. So now our integral here, after our u substitution, looks like this. And this we know how to find. So once you've done that, hopefully you'll see that the surface area is equal to pi over 9 times the square root of, well, yeah, times 17 times the square root of 17 minus 1.